Hello everybody. So, on today's videos, we're going to be talking about tangent lines, linear approximations, and the chain rule. Now, this is basically going to be the same type of stuff as we had back in Calc 1. But just adding the extra dimensions do change things a little, but it's not a ton. So let's go ahead and get right into it. First of all, a tangent plane. Well, if you're dealing with a huge surface, you're not really going to have a tangent line anymore. You're going to end up dealing with tangent planes. So the tangent plane at a point on a function is the plane that contains all tangent vectors at that point. So in class we talked about how you could draw a curve going to the point, and there's an infinite number of possible curves that could go in that direction. So that means every single one of those curves has a tangent line or tangent vector. So if you end up finding out all of them, they'll all be on the same plane, so long as it is a nice smooth function. If it's not a smooth function, you're out of luck. But in general, as long as you can find two of them, well, if you know two vectors that are in a plane and they're not parallel with each other, then find the cross product. That gives you a normal vector. You already know what the point is. You can find the equation there. Now, there's a slightly easier way to do it with this formula down here. So, as long as the partials exist at that point, you can find your tangent plane formula. Alright, so it's useful. That way you don't have to go through the full process of finding the cross product and going from there. Now, here's a quick example of what it looks like. So, just like with a tangent line, really close to the point, it's a good approximation. The further away you get, it gets a lot worse. So that's where the linear approximation comes in. So you can use the tangent plane to approximate for your function close to the point. There's no real reason to do that anymore. It's just one of those things that was easier when you didn't have a calculator or a computer. Everybody does now. There's no real reason to worry about linear approximation much. Now, but there's a theorem that comes somewhat from it that is still useful. So it states that if the partials exist near a point, and the partials are continuous at that point, then the function itself is differentiable at that point. This is a very useful theorem. Now, to show that they exist at that point, well, that's not too hard. To show that they are continuous at that point, as we talked about in class, that gets a lot trickier. So that's always going to be the tough part to show, but as soon as you can show that, you show differentiable. Now, the other thing we have to keep in mind is differentials. So for differentials, it's more we're talking about small little changes in x, y, and z. And it's a situation where choose the difference in your x and choose the difference in your y, and that'll tell you what the difference in z should end up being. That's essentially how this is going to end up working out. So going back to a situation of like you're working in a factory. Well, if we increase the amount of iron we use for this particular product and we slightly decrease the amount of sulfur we use, what's the final product cost going to be? That's the type of situation where this would still get used. Alright, now on to the chain rule. So hopefully you all remember the chain rule from Calc 1. And it stays about the same. This one, it's a setup where if x is a function of its own, y is a function of its own, but x and y are a function inside of z, you can end up using the chain rule to find dz dt. And it should work exactly as you expect it to. Alright? Hopefully it's informative for you guys, and see you in class.